For 72 seconds in 1977, a radio telescope in Ohio heard something from deep space, something that shouldn't have been there. Then it was gone. 50 years later, no one has heard it again, and the only proof is a single page. I'm Ray, and this is Longwave Sky. I've been quietly obsessed with this one signal since I was a kid. Tonight, we'll sit with it slowly. If these quiet journeys help you sleep, a like and subscribe help others find them. So, let's go back. August 1977. A warm night in rural Ohio, and a telescope the size of 3 football fields, listening. The telescope was called Big Ear. It didn't look at the sky. It listened to it, patiently, night after night. It belonged to Ohio State University, part of one of the longest searches ever made for a signal from another world. Its job was simple and almost impossibly patient: to catch a whisper of radio from somewhere far out in the dark. There were no screens, no alarms, no one watching live, just a computer printing numbers onto paper, hour after hour. Each number was a measure of how loud the sky was, in one narrow sliver of radio, moment by moment. Most of the time, the sky was quiet, page after page of low numbers, the soft, steady hiss of an empty universe. And so, the telescope drifted, letting the Earth's own turning sweep its gaze slowly across the stars. On the night of August 15th, it swept past a quiet corner of the sky in the direction of Sagittarius. Nothing seemed to happen. The paper kept printing. The room was empty, and the signal came and went, unseen. 3 days later, a volunteer astronomer named Jerry Eamon sat down with the stack of printouts to check them by hand. It was slow, unglamorous work. Columns of numbers, line after line, looking for anything that rose above the noise. And then, in one column, he found it. A sequence that didn't belong. 6 characters, climbing far above everything around them. 6 EQUJ 5. He circled them in red pen, and in the margin, he wrote a single word: wow. That printout still exists. That red circle, that one word, is the closest thing we have to a photograph of the signal. But to understand why he wrote it, you have to understand what those 6 characters actually meant. The numbers weren't a message, they were a scale, a code for intensity, for how strong the signal was each moment. 0 was quiet, 9 was loud, and when a signal was louder than 9, the printer ran out of numbers and used letters. So the sequence 6 EQUJ 5 was really a shape. A signal rising, climbing past the letters, then falling away. It peaked at U, a level the telescope almost never saw, 30 times stronger than the quiet hum of the background sky. And the shape of that rise and fall was the strangest part. It lasted almost exactly 72 seconds. That number wasn't random. 72 seconds was exactly how long the telescope's gaze took to drift past a single point. In other words, the signal behaved perfectly. It grew as the telescope swung toward it and faded as it swung away. That's what a real source in deep space would look like. Not interference from Earth, not a glitch, something out there. So the next question was the obvious one. Where exactly had the telescope been pointing at that moment? The answer was a patch of sky in the constellation Sagittarius, toward the crowded heart of our own galaxy. A region thick with distant stars, far beyond anything we could reach, and no known object that should have made a sound. But the direction wasn't even the strangest detail. The strangest detail was the exact frequency of the signal. Radio covers an enormous range. The signal sat almost perfectly on one specific note, near 1,420 megahertz. That frequency has a name. It's the hydrogen line, the natural hum given off by the most common element in the universe. Hydrogen is everywhere, so astronomers had long guessed that if anyone ever tried to call out, they might choose that frequency. A frequency any curious civilization anywhere would know. A natural place on the dial to listen for company. And the wow signal landed almost exactly there. Right on the one note we'd expect a deliberate message to use. It was also astonishingly pure, packed into a band so narrow that nature has a very hard time explaining it. Natural sources tend to smear across many frequencies. This was sharp, focused, the kind of thing a transmitter makes. Everything about it lined up. The shape, the strength, the direction, the frequency. It all pointed the same uneasy way. So the astronomers did the only responsible thing. They turned the telescope back to that same patch of sky and waited. If it was a beacon, it might repeat. If it was a passing ship of some kind, it might come around again. They looked again the next night, and the night after. Eamon pointed the telescope back more than 50 times over the years. Other observatories joined in, with dishes far more sensitive than Big Ear had ever been, all of them listening to that spot. And every single time, they heard the same thing. Nothing. The quiet hiss of an ordinary empty patch of sky. The signal never came back. Not once in nearly 50 years of listening. It arrived, it spoke for a minute, and it left. And that is what makes it so hard to let go of. A one-time event can't be proven, and it can't be dismissed. Too clean to be a mistake, too brief to ever explain, sitting in that strange space between coincidence and contact. Over the years, people have tried to solve it. Comets, satellites, distant clouds of hydrogen quietly brightening. Tonight, we're going to walk through every one of those explanations, slowly, and see which of them actually holds up. The simplest explanations are usually the boring ones. Before reaching for anything strange, scientists asked a quieter question first. Could the signal have started right here on Earth? Our own planet, after all, is anything but quiet. From orbit, Earth glows with electronics, broadcast towers, radar stations, satellites, all talking constantly in radio frequencies. Every night, thousands of signals cross the sky above Big Ear, reflections, stray transmissions, echoes bouncing off machinery that was never meant to reach a telescope at all. So investigators began working backward, testing every ordinary source they could think of, one by one, hoping the mystery would collapse into something forgettably mundane. The first suspect was radar, powerful military and civilian dishes capable of throwing a signal for hundreds of miles, sometimes bouncing unpredictably off the atmosphere itself. But radar operates on frequencies far from the hydrogen line the WOW signal used, and no facility nearby was transmitting anywhere close to that exact number. Next came aircraft, a passing plane's transponder pulsing on the right frequency, caught for exactly the length of one overhead pass, then gone. Except transponder signals repeat in short, regular bursts, nothing like the slow 30-second rise and fall Jerry Eamon found printed on that page. Then there were satellites, hundreds already circling Earth by 1977, any one of them capable of reflecting a stray ground signal straight back down. Satellites move fast, though, and their signals drift in frequency as they pass. This signal didn't drift at all. It held remarkably, unnervingly still. One by one, the ordinary explanations were tested against the data, and one by one the printout refused to match any of them cleanly. Whatever this was, it didn't behave like the noisy, restless technology humans had built to orbit their own world. With Earth ruled out, attention turned outward towards smaller, colder wanderers, comets, quietly drifting through the outer edges of the solar system. In 2016, an astronomer named Antonio Paris proposed something unexpected, that a comet, not a signal from deep space, might explain everything. Comets carry invisible clouds of hydrogen around their icy nuclei, vast envelopes stretching millions of miles, faint and cold and easy to overlook. If that hydrogen cloud happened to glow at exactly 1420 megahertz, a passing comet could, in theory, mimic a narrow radio burst. Paris pointed to two specific comets, 266P and 335P, calculating that both may have crossed near that patch of Sagittarius decades later. It was an elegant idea. Cold, unremarkable ice replacing an impossible mystery, tidy enough that for a while, many people wanted to believe it. But an elegant idea is not the same as a confirmed one, and elegance alone has never been enough in astronomy. When other astronomers pointed their instruments at those same comets during their actual predicted passes, they listened for hours. They found nothing, no matching burst, no hydrogen signature anywhere near the strength required to produce what Big Ear had recorded. The comet hypothesis, however tidy, quietly failed the one test that mattered most. It didn't reproduce the signal. More recently, in 2024, a new idea emerged from an old and overlooked source: the hydrogen gas drifting between the stars themselves. Vast, cold clouds of hydrogen fill much of our galaxy, usually silent, usually invisible except in radio wavelengths astronomers know well. Under rare conditions, a nearby magnetic field can excite that hydrogen, pumping it briefly into something like a natural laser, a masser. For a few fleeting seconds, an ordinarily silent cloud could brighten enormously, radiating far more strongly than its usual gentle background hum. If such a flare passed directly through Big Ear's narrow beam, it could, in theory, produce exactly the rise and fall Eamon recorded. It's a genuinely elegant physical mechanism, grounded in real astrophysics, not speculation about circuitry or ice. But elegant does not mean proven. No one has ever directly observed this kind of hydrogen flare happening in real time. The 2024 paper offers a hypothesis, a plausible natural explanation, not a confirmed answer to what happened that August night. These flares, if they're real at all, would be exceedingly rare, which raises an uncomfortable question none of the other explanations answer either. If the source really was something this rare, why has nothing quite like it ever been recorded again, anywhere, in almost 50 years? That question brings us back to Big Ear itself, which kept listening to that same patch of sky for years afterward. Jerry Eamon personally searched the archive data dozens of times, hoping the signal might simply be hiding in plain sight, waiting to repeat. It never did. Not once, not faintly, not in any of the tens of thousands of hours the telescope kept recording that region. Decades later, far more sensitive instruments joined the search, arrays capable of hearing signals thousands of times fainter than Big Ear ever could. The Very Large Array pointed its dishes toward Sagittarius. The Allen Telescope Array, built specifically for this kind of search, listened for months. Every one of those searches returned the same result: silence. Vast, patient, undisturbed silence, exactly where the signal had once briefly appeared. 50 rescans and counting, across nearly 5 decades, and the number of confirmed repeats remains exactly 0. So we're left with a single sheet of paper, 6 characters long, and absolutely nothing else to compare it against. I'll admit, that's the part that gets me. Not the mystery itself, but the silence afterward. The not knowing if we'll ever get another chance to check. Every ordinary explanation fits a little, and none of them fit completely. Earth's noise, an icy comet, a rare stellar flare, each one close, none of them whole. Maybe that's simply how first contact would look, if it ever really happened. Brief, accidental, and never repeated cleanly enough to prove. Or maybe it's something we genuinely haven't imagined yet, some natural process still waiting for its own name and explanation. Either way, the signal did exactly what a real signal from a real distant source should do. It rose, it peaked, and it faded. It behaved, in other words, exactly like something actually out there, which is precisely why, after 50 years, no one can quite let it go. The wow signal was never really the whole question. It was only ever the loudest, most specific reason to ask a much older one. Are we really alone out here, scattered across one ordinary galaxy among hundreds of billions, listening into a silence that occasionally, briefly, answers back? Every star, every quiet hydrogen cloud, every one of these worlds we've been drifting past tonight might already be asking the exact same question. For now, all we have is one recorded moment, one narrow band of radio noise, and an open sky that has never fully closed the case. The question of whether we're alone didn't start with a telescope printout. It started decades earlier with one astronomer trying to put a number on hope itself. In 1961, Frank Drake gathered a small group of scientists at Green Bank, West Virginia, to ask a single, almost impossible question out loud. How many civilizations right now might be sending signals of their own across our galaxy, close enough for us to actually hear them? Drake wrote it as an equation: star formation rate multiplied by planets, multiplied by habitability, multiplied by life, multiplied by intelligence, multiplied by time. Every term in that equation was, and still is, mostly a guess. Some can now be estimated. Most remain almost entirely unknown. Multiply enough uncertain numbers together, though, and the equation still points somewhere real. The odds of us being the only ones seem, at minimum, strange. That meeting in 1961 didn't answer the question. It simply gave the search a name: the Search for Extraterrestrial Intelligence, SETI. From that point on, listening to the sky stopped being a hobby and quietly became a real, funded, scientific pursuit. 13 years later, in 1974, one radio telescope decided to stop only listening and try, just once, actually speaking back. The Arecibo Observatory, its enormous dish built into a natural sinkhole in the hills of Puerto Rico, was the largest radio telescope on Earth at the time. For its rededication ceremony, astronomers built a message, a simple picture of numbers, DNA, our solar system, and a human figure encoded in radio pulses. The message lasted under 3 minutes. It was aimed at M13, a dense cluster of roughly 300,000 stars, 25,000 light-years away. At that distance, even traveling at the speed of light, the message won't arrive for another 24,000 years or so. A reply, if anyone out there chose to send one back immediately, wouldn't reach Earth for nearly 50,000 years after that. It was never really meant to get an answer. It was a demonstration, proof that if we wanted to speak, we technically could. Which raises the same question every SETI signal eventually returns to. If something out there wanted to speak to us, would we even recognize it in time? Over the decades since, that recognition has happened, or almost happened, more times than most people realize. In 1997, an object cataloged only as a faint radio blip appeared briefly in SETI data, unexplained for hours before quietly being traced to a satellite. In 2003, another signal, later nicknamed simply the blip, showed up in archived Arecibo data during a home computer search project and was never fully explained. Volunteers running SETI at home, a program that used ordinary people's computers to analyze radio data, flagged it as one of the strangest signals in the whole archive. It appeared only once in a narrow frequency band from a patch of sky with no known planet close enough to explain it. Follow-up observations, like the ones aimed at the WOW signal decades earlier, found nothing there when astronomers looked again. Most of these cases end exactly the same way. A single detection, real and recorded, that quietly refuses to happen a second time. It's tempting to read failure into that pattern, but absence of repetition isn't the same as absence of meaning. It's simply the hardest kind of evidence to work with. Each unexplained blip becomes another entry in a long, patient list, filed under neither solved nor disproven, waiting for better instruments or better luck. And so the search continues, mostly finding silence, occasionally finding something stranger than silence, and only rarely finding real answers. All of this circles back to a much older, blunter question, first asked plainly over lunch by physicist Enrico Fermi in 1950. If the universe is truly this vast and this old, and life is even remotely common, Fermi asked simply, where is everybody? The math seems to favor company. Billions of stars, billions of years, countless chances for intelligence to rise and eventually reach outward. And yet, after decades of careful listening, the numbers keep returning the same uncomfortable answer. Nothing confirmed, nowhere, not once. Scientists call this contradiction the Fermi paradox, the gap between how likely company seems on paper and how empty the sky actually sounds. There's no shortage of proposed solutions. Maybe intelligent life is rarer than we assume. Maybe it doesn't last long enough to be noticed. Maybe civilizations simply stop broadcasting once they no longer need to, moving to communication methods we haven't learned to detect at all. Or maybe, as with the WOW signal itself, someone already did reach out once, briefly, and we simply weren't listening at exactly the right moment. One star, far from our solar system, would later reignite this whole conversation in an entirely different, stranger way. Astronomers call it KIC 8462852. Almost everyone else just calls it Tabby's star, after the researcher who first flagged its behavior. In 2015, data from the Kepler Space Telescope showed this ordinary-looking star dimming by unusually large, irregular amounts, again and again. Planets dim a star's light in small, clean, predictable dips as they pass in front of it. This star's dimming was neither small nor predictable. At its most extreme, Tabby's star dimmed by over 20%, far too much for any single planet, however large, to explain on its own. For a brief, genuinely serious moment, some scientists floated an extraordinary idea, a vast artificial structure built to capture a star's energy directly. Follow-up studies eventually favored a quieter answer, an uneven cloud of orbiting dust, unusually dense and irregularly shaped, but entirely natural. Even so, the dust explanation took years of careful, painstaking work to establish, and even now a few smaller irregularities remain only partly explained. The most recent serious contender in this long story came not from an old archive, but from our very nearest stellar neighbor. In 2020, the Parkes Radio Telescope in Australia picked up a narrow, persistent signal while observing Proxima Centauri, just over 4 light-years away. Researchers designated it BLC-1, short for Breakthrough Listen Candidate 1, and quietly spent over a year testing it before saying anything publicly. For a while, it passed every test that should have ruled out human interference, a real signal, from the right direction, at a suspicious frequency. Eventually, careful analysis traced its subtle frequency drift to a pattern consistent with ordinary equipment on the ground, not with Proxima Centauri at all. Another candidate, tested seriously and honestly, quietly returned to the same long list of near misses that came before it. I keep coming back to that list, honestly. Not because any single entry proves anything, but because of how seriously each one was actually checked. Nobody in this story wanted to believe carelessly. They wanted proof. And that, more than any single signal, might be the most human part of this whole search. Proving any signal real, though, takes more than one excited moment at a telescope. Astronomers built an entire process just for judging how seriously to take a claim. In 2000, researchers proposed something called the Rio scale, a simple number, 0 to 10, meant to rate exactly how significant a possible extraterrestrial signal actually is. It weighs the signal's strength, its distance, how easily it could be explained by something ordinary, and how much of a stir it would genuinely cause if confirmed. Almost every candidate signal in this story, including the WOW signal itself, would score only moderately on that scale. Interesting, but nowhere near proof. A true confirmation would require something else entirely. An independent telescope, somewhere else on Earth, catching the very same signal at the very same moment. That's the step most candidates never survive. A single detection, however striking, is only ever a beginning, never an ending. But not every strange radio discovery in astronomy's history stayed unexplained forever. Some of the strangest ones actually did get solved. One of those stories starts not with a signal from the stars, but with a graduate student, a mountain of paper, and a pattern nobody expected. In 1967, at Cambridge University, a young astronomer named Jocelyn Bell Burnell was combing through miles of chart paper from a new radio telescope. Buried in the noise, she found something strange, a signal pulsing with almost impossible regularity, once every 1.3 seconds, over and over. The pulses were so precise, so mechanically perfect, that Bell Burnell and her supervisor half-jokingly nicknamed the source LGM1, Little Green Men. For a few private weeks, before telling anyone outside the lab, they genuinely wondered if they'd found a beacon built by someone else. Then Bell Burnell found a second, completely different pulsing source in an entirely different part of the sky, behaving the exact same way. One artificial beacon might be believable. Two, from unrelated directions, both behaving identically, pointed towards something far stranger, a natural process no one had seen before. The real answer turned out to be a spinning neutron star, the collapsed core of a dead star, city-sized, impossibly dense, spinning many times each second. As it spins, it sweeps a beam of radio energy across space like a lighthouse, and each time that beam crosses Earth, we catch one precise pulse. Astronomers named this new class of object a pulsar. Bell Burnell had discovered an entirely new kind of star, hiding in what first looked like an alien signal. It's a genuinely reassuring story in its own way. The signal was strange, the pattern was mechanically clean, and the explanation, once found, was airtight. That's precisely why pulsars matter to this whole conversation. They prove the universe really can produce something clean and regular, purely by accident of physics. Which means every time a signal looks artificial, astronomers now have to seriously ask, is this another little green men moment, or is it actually something new? Sometimes, as with pulsars, the honest answer turns out to be natural after all. Sometimes, as with the WOW signal, the honest answer is still simply, we don't know. And sometimes the sky offers a signal that resists both answers for years at a time, genuinely too strange to explain and too real to dismiss. In 2007, an astronomer named Duncan Lorimer was reviewing old pulsar data when he noticed something that didn't belong in the archive at all. A single, incredibly bright burst of radio energy, lasting only a few milliseconds, far more powerful and far shorter than anything a pulsar should produce. It became known as the Lorimer burst, the first confirmed example of what astronomers now call a fast radio burst, or FRB. Unlike the WOW signal, this burst carried a strange fingerprint. Its frequencies arrived slightly staggered, delayed exactly the way a signal is delayed after crossing vast amounts of intergalactic gas. That delay told astronomers something remarkable. Whatever caused this burst wasn't inside our galaxy. It came from billions of light years away, from another galaxy entirely. To release that much energy, in that little time, across that much distance, the source had to be almost unimaginably powerful, even by cosmic standards. For years, nobody could agree on what caused it. Colliding neutron stars, evaporating black holes, and yes, more than a few papers seriously discussed artificial origins. Then, in 2012, astronomers found something even stranger, a fast radio burst that didn't just happen once. It repeated, again and again, from the exact same point in the sky. This repeating source, cataloged as FRB121102, ruled out any single violent one-time event. Whatever it was, it could produce these bursts over and over for years. Some astronomers, including the well-known theorist Avi Loeb, seriously floated the idea of an artificial explanation, a vast alien structure using focused radio beams to power distant starships. It was a genuinely serious scientific proposal, published and peer-reviewed, not idle speculation. A real demonstration of how open this particular mystery still was. The more likely, more grounded explanation eventually pointed to magnetars, neutron stars with magnetic fields trillions of times stronger than anything found on Earth. Under the right conditions, a magnetar's crust can crack and shift, releasing a sudden, enormous burst of energy across radio frequencies in an instant. In 2020, astronomers caught a magnetar inside our own galaxy doing exactly that, producing a burst that looked remarkably like a smaller, closer cousin of an FRB. That single detection gave the magnetar theory real, direct evidence for the first time, rather than just an educated guess built from distant, indirect data. But one confirmed local example doesn't explain every fast radio burst ever recorded. Thousands have now been cataloged, and their behavior isn't perfectly uniform. Some repeat on strict, almost rhythmic schedules, Others fire once and vanish completely. A few show patterns that still don't fit the magnetar model cleanly. So the honest current answer sits somewhere uncomfortable. Magnetars almost certainly explain many fast radio bursts, but probably not quite all of them. Which means, once again, after all the physics and all the observation, a version of the same old question returns. What exactly are we still missing? The universe, it turns out, is genuinely full of things that sound artificial at first and later prove to be natural, and a few that still haven't decided which they are. I find that oddly comforting, honestly. Pulsars once looked like little green men. Fast radio bursts once looked like alien starship engines. Most mysteries do eventually resolve. Most, but not quite all. The wow signal is still exactly where it started nearly 50 years ago, recorded once, never repeated, never fully explained. Maybe someday a future Jocelyn Bell Burnell finds the real, ordinary explanation buried in some overlooked data set, and the mystery quietly closes for good. Or maybe it simply never gets solved, and that unfinished feeling becomes part of what makes it worth remembering at all. Either way, the sky keeps offering both kinds of answers, the reassuringly natural and the genuinely, patiently unresolved. For now, Big Ear is gone, the field where it stood repurposed long ago, but the signal it caught that August night is still exactly what it always was. 6 characters, 72 seconds, one narrow frequency, and a question that has outlived the very telescope that first heard it. We'll keep listening. Somewhere between the pulsars we've explained and the bursts we're still chasing, that's really all any of this search has ever been. Not every mystery arrives as a signal, though. Sometimes the universe sends something you can actually watch move, and that turns out to be its own kind of puzzle. In October 2017, a telescope in Hawaii called Pan-STARRS caught a faint point of light crossing the sky at a genuinely strange, impossibly fast speed. Astronomers tracked its path backward and found something that had never been confirmed before. This object wasn't born in our solar system at all. It had come from interstellar space, passed briefly through our neighborhood, and was already leaving, never to return. They named it Oumuamua, a Hawaiian word roughly meaning scout or messenger reaching out from the distant past. It was the first interstellar object ever confirmed passing through our solar system, and almost immediately it started behaving strangely. Most objects like this are comets or asteroids, and both usually announce themselves clearly. Oumuamua refused to fit either category cleanly. The stranger its behavior got, the more seriously astronomers had to ask an uncomfortable question. What, exactly, were they actually looking at? The first oddity was its shape. Based on how its brightness flickered as it tumbled, Oumuamua appeared to be extremely elongated, far more than any known asteroid or comet. Some estimates suggested it was 10 times longer than it was wide, closer to a cigar or possibly a flattened pancake than anything typically found drifting through space. Natural objects can be irregular, but rarely that extreme. Nothing in our own solar system looks quite like the shape astronomers were calculating. The second oddity was how it tumbled. Oumuamua wasn't spinning smoothly on one axis. It was rotating chaotically, end over end, in an unusually complex way. The third and strangest oddity came from watching its exact path. As it left our solar system, Oumuamua sped up slightly more than gravity alone could explain. Endaking. Comets do this too sometimes, but only because ice on their surface heats up and jets outward, pushing the comet forward like a tiny, uneven rocket. The problem was, nobody could see any of that happening. No glowing coma, no visible tail, no dust cloud. The telltale signature comets always leave behind. An invisible push with no visible cause on an object shaped unlike anything else ever recorded. Each fact alone was strange. Together, they were something else entirely. Astronomers only had a matter of weeks to study it before Oumuamua sped back out of range, moving too fast for any spacecraft to ever catch up. No follow-up mission was possible, no second look. Whatever answers existed, they had to come entirely from the data already gathered during that brief window. For an object behaving this strangely, that narrow window left far more open questions than the astronomy community was used to living with. Every proposed explanation had to somehow account for all three oddities at once: the extreme shape, the chaotic tumble, and the unexplained acceleration. That combination, plausible individually, deeply strange together, is exactly the kind of pattern that eventually pulls in more than just careful skepticism. It pulls in genuinely serious scientists willing to ask the question most of astronomy prefers to avoid saying out loud. One of those scientists was Avi Loeb, chair of Harvard's astronomy department. Not a fringe figure, but one of the field's most established voices. Loeb argued that the unexplained acceleration, without any visible outgassing, fit one explanation astonishingly well: sunlight pressure pushing against an extremely thin, artificial sail. A light sail, he proposed, a technology humanity has already designed on paper, thin enough and light enough to be pushed gently forward by starlight alone. If Oumuamua were an extremely thin sheet, its exaggerated shape and its mysterious acceleration would both be explained by the exact same simple cause. In 2021, Loeb published a book laying out the full case, arguing that Oumuamua deserved serious consideration as possible extraterrestrial technology, not casual dismissal. The reaction from much of the astronomy community was immediate and sharply divided, some intrigued, many openly skeptical, a few outright dismissive. Most astronomers agreed the acceleration was real and needed explaining. Very few agreed that an alien light sail was the most reasonable place to start. Their objection wasn't emotional, it was methodological. Extraordinary claims require exhausting every ordinary explanation first, however incomplete or inconvenient those explanations turn out to be. And Oumuamua, they pointed out, was only the first confirmed interstellar visitor. Statistically, it was unlikely to be uniquely engineered rather than simply unfamiliar. The debate became unusually public for astronomy, argued in journals, conferences, and headlines, watched closely by people who had never followed a research dispute before. It also became a genuine test case for this whole channel's honest approach. How do you weigh a serious hypothesis against the deep discomfort of taking it seriously? Loeb's critics weren't wrong to demand more evidence. Loeb wasn't wrong that dismissing the idea outright, without real justification, was its own kind of bias. Science is supposed to hold both of those truths at once, uncomfortable as that balance can feel when the question is this large. For a while, Oumuamua sat exactly there, unresolved, contested, too strange to explain and too serious a mystery to simply wave away. Then, in 2021, two astronomers, Darrell Seligman and Gregory Laughlin, proposed a purely natural mechanism that hadn't been seriously modeled before. Their idea centered on frozen molecular hydrogen, ice that could form only in the extreme cold of deep interstellar space, long before Oumuamua ever neared our sun. As Oumuamua approached sunlight for the first time in perhaps billions of years, that hydrogen ice could sublimate directly into gas, invisibly, without forming a visible coma. Unlike the water ice jets on a typical comet, hydrogen outgassing wouldn't glow, wouldn't scatter sunlight the same way, and could easily go completely undetected by telescopes on Earth. That invisible venting, the model showed, could produce exactly the kind of gentle, unexplained push scientists had measured. No light sail required, no visible tail required. It was an elegant answer, grounded entirely in known physics, and it quickly became the explanation most cited in mainstream astronomy circles. But elegant, once again, doesn't mean proven. Nobody has ever directly observed hydrogen ice forming or outgassing on any real interstellar object, Oumuamua included. The model works on paper. Whether it's what actually happened out past Jupiter's orbit in late 2017 remains a calculation rather than a confirmed observation. Itam. So Oumuamua's file closes the same way the WOW signals does, with a leading, reasonable, mostly accepted natural explanation and no way left to fully confirm it. The object itself is already gone, moving silently back into interstellar space, carrying its real answer somewhere no telescope on Earth will ever follow. I think that's the part of this whole search I keep circling back to, honestly. we rarely get to simply know. We get our best current guess, and we move forward. A pulsar, a fast radio burst, an interstellar visitor, one narrow signal from Sagittarius, each one taught us to hold curiosity and doubt in the same hand. Maybe that's the actual skill this search has been quietly teaching for 50 years. Not certainty, but the patience to keep looking without needing an answer right away. Somewhere out past what any of our telescopes have reached yet, something else is almost certainly still passing through, still waiting to be noticed. We'll be listening. If there's one person whose entire life became tangled up with a single radio printout, it's not Jerry Eamon himself. It's a man named Robert Gray. Gray wasn't a professional astronomer. He was an amateur, a working engineer who read about the WOW signal not long after it happened and simply couldn't let it go. In 1995, nearly 2 decades after Eamon found the signal, Gray did something almost nobody else had bothered to do. He pointed a real telescope at the exact same coordinates himself. He used a private radio dish, and later time on much larger professional instruments, always aimed at that same small patch of sky in Sagittarius. His first attempt found nothing. So did his second. He kept going anyway, treating each null result not as failure, but as one more data point worth having. In 1997, Gray gained access to the Very Large Array in New Mexico, one of the most sensitive radio observatories on Earth, and pointed it toward Sagittarius again. Still nothing. The silence Big Ear had already logged for years held true even under instruments many times more powerful than the one that first caught the signal. Most people would have stopped there. Gray didn't. Over the following decades, he kept returning to the same question, the same coordinates, the same quiet sky. By the early 2000s, he had teamed up with professional astronomers for more formal published searches, lending his amateur persistence real scientific structure. What kept him going wasn't hope for a repeat exactly. It was the simple fact that nobody had ever actually closed the file. The question was still technically open. In 1999, Gray and astronomer Simon Ellingson used the MOPRA radio telescope in Australia for another dedicated search, 6 separate observing sessions aimed squarely at the signal's coordinates. They found no repeat, but their careful published methodology helped establish something valuable. The strictest, most credible non-detection results the search had produced so far. In 2002, Gray returned to the Very Large Array one more time, this time with even greater sensitivity than his 1995 attempt, for another dedicated quiet check. Once again, the sky offered nothing, but a null result, published properly, still narrows the possibilities. It rules out entire categories of explanation, even without an answer. By ruling out anything that repeats on any regular detectable schedule, Gray's searches quietly strengthened the case that whatever caused the signal was genuinely a one-time event. That's an uncomfortable kind of progress, real, careful, published work that mostly proves what the signal wasn't, rather than what it was. In 2012, Gray gathered everything, his own searches, Eamon's original data, every competing hypothesis, into a book called The Elusive WOW. It remains one of the most thorough single accounts of the entire signal ever assembled, written not by a distant academic but by someone who had spent decades personally chasing it. Gray's own conclusion after all that searching was carefully measured. He never claimed to have solved it. He argued instead that it deserved to stay seriously unsolved. In his view, dismissing the signal as probably terrestrial without stronger evidence was just as unscientific as assuming it was definitely alien. The honest answer, Gray insisted, was the hardest one to sit with, genuinely unknown, and likely to remain that way without new data nobody currently has. It's worth pausing on what kind of persistence that actually took. Decades of applying for telescope time, writing proposals, defending a search most colleagues considered a long shot. Nobody funded Gray to do this. Nobody assigned it to him. He simply decided the question mattered enough to spend a meaningful part of his life chasing it. That's not really a scientist's story, or even purely an astronomer's story. It's the story of stubborn, patient curiosity, refusing to accept a question as closed. In a strange way, Robert Gray became the signal's actual custodian. Not the man who found it, but the man who refused to let it be forgotten. His work also quietly influenced how later, larger SETI efforts treated old, unrepeated signals, not as curiosities to file away, but as data still worth revisiting. When Breakthrough Listen launched in 2015, backed by serious funding and modern instruments, the WOW signal was one of the historical cases its founders specifically cited. Breakthrough. Listen re-observed Sagittarius using the Green Bank telescope, one of the most sensitive radio telescopes ever built, searching a far wider range of frequencies than Big Ear ever could. Once again, across that wider search, nothing matched. No narrowband signal near 1420 MHz, no repeat of the pattern Eamon found on that page in 1977. Each new search, using each new generation of technology, adds one more careful, well-documented layer to the same conclusion. It happened once and only once. Some researchers now treat that consistency itself as meaningful, not proof of anything exotic, but proof that the original detection was almost certainly real, not equipment error. A one-off glitch in outdated 1970s hardware wouldn't likely survive this many independent rechecks across 5 decades of steadily improving technology. Whatever produced that signal on that one August night was real enough, external enough, and precise enough to still be worth this much sustained attention. That's the strange legacy Robert Gray helped build. Not an answer, but a permanent, well-documented case for taking the question seriously, generation after generation. Every few years now, a new team, a new instrument, a new graduate student revisits the same coordinates, the same 1420 MHz line, the same 72 seconds. None of them expect to find anything exactly, but none of them are willing to be the generation that simply stopped checking. It's an unusual kind of scientific inheritance, not a solved problem passed down, but an open one, tended carefully so it never quietly disappears. Robert Gray passed away in 2022, having spent nearly half a century of his life connected, in one way or another, to a single signal he never personally received. He never got his answer. He got something else instead. A permanent place in the story of the one signal that came closest to changing everything and never explained itself. In interviews late in his life, he said he had made peace with that outcome. The search itself, he said, had been worth doing, regardless of what it ever found. I think about that a lot, honestly. The idea that looking can be worth something even when it never resolves into an answer. Robert Gray spent decades listening to the same quiet patch of sky, and in a strange way, that makes him a kind of distant cousin to every person watching this right now. You don't have to be a professional to care about a real, unanswered question. You just have to be willing to keep paying attention long after most people have moved on. That's honestly the whole spirit behind this channel too. Not chasing certainty, but sitting comfortably inside the not knowing a little longer than feels entirely comfortable. The WOW signal is still exactly what it was in 1977. 6 characters, 72 seconds, one narrow frequency, and a silence nobody has ever fully explained. Every telescope that's pointed back at that patch of Sagittarius has added another entry to the file and closed none of it. Somewhere in an archive, Jerry Eamon's original printout still exists, the word WOW still circled in red pen exactly as he left it that day. And that unanswered question is exactly why the search around it kept expanding into new telescopes, new signals, and new questions that all trace back to this same one origin. Because once you start taking one unexplained signal seriously, you start noticing how many other pieces of the sky are still waiting for the same kind of attention. So we'll keep circling back to Sagittarius, and to everything nearby it taught us to look for. The story isn't finished. It's just getting started. Every time we've mentioned Sagittarius in this story, we've been pointing at one small, specific patch of a much larger, much stranger neighborhood. Because roughly 26,000 light-years away, in that exact same general direction, sits the actual center of our entire galaxy. Not just stars, not just gas. Something far heavier is quietly waiting there. Radio astronomers first noticed something unusual coming from that region back in 1974, decades before anyone confirmed what it really was. Two researchers, Bruce Ballack and Robert Brown, detected a compact, unusually bright source of radio waves buried deep in the galactic core. It didn't behave like a star, a nebula, or anything else astronomers had cataloged before. It was small, intense, and strangely quiet most of the time. In 1982, the source finally got a name, Sagittarius A star, marking it as the single most important radio object at the galaxy's heart. For years, nobody could actually prove what it was. The leading suspicion, almost from the start, was the most extreme object physics allows, a supermassive black hole millions of times heavier than our sun. But suspicion isn't proof, and in astronomy, proving something you can never directly see takes an entirely different kind of evidence. That evidence came from an unlikely source, not the black hole itself, but the ordinary stars orbiting dangerously close around it. In the early 1990s, two separate research teams began an extraordinarily patient project, tracking individual stars near the galactic center year after year. One team was led by Reinhard Genzel in Germany. The other, working independently, was led by Andrea Ghez in the United States. Both teams used the largest telescopes on Earth, fighting through thick interstellar dust that blocks ordinary visible light from ever reaching us. Infrared light, though, passes through that dust far more easily, and infrared is exactly what both teams used to see through to the galactic core. One star in particular became the key to everything, a bright, fast-moving star astronomers designated simply S2. S2 orbits something completely invisible, and it orbits remarkably fast. Genzel's and Gez's teams tracked S2's position year after year, plotting a single, elegant, curving path around an object nobody could actually see. By the mid-2000s, both teams had independently mapped enough of that orbit to calculate something staggering about whatever S2 was circling. Whatever sat at the center of that orbit weighed roughly 4 million times the mass of our own sun, compressed into an impossibly small volume. No known star, star cluster, or ordinary object could explain that much mass packed into that little space. Only one candidate fit the numbers. A supermassive black hole, not a suspicion anymore, but a conclusion, built patiently from 20 years of careful, repeated observation. In 2020, Genzel and Ghez shared half of that year's Nobel Prize in Physics for exactly this discovery, decades of watching one small star's orbit. The black hole itself finally had a name too, Sagittarius A star, the same designation given to that mysterious radio source back in 1982. It turned out the strange, quiet radio signal from decades earlier and the invisible mass bending S2's orbit were the exact same object. One mystery had quietly become two mysteries, solved together at last. Even with the mass confirmed, though, nobody had ever actually seen the black hole itself. Nobody had a picture of it. Black holes, by definition, emit no light of their own. What you can photograph, in theory, is the shadow they cast against the glow around them. That glow comes from superheated gas spiraling toward the black hole, gas so hot and energetic it radiates brightly just before disappearing forever. Photographing that faint shadow from 26,000 light-years away meant building something no single telescope on Earth could ever achieve alone. The solution was the Event Horizon Telescope, not one instrument but a coordinated network of radio dishes spanning the entire planet at once. By linking observatories from Antarctica to Hawaii to Spain, astronomers effectively built a telescope the size of Earth itself. In April 2019, that global network released its first ever image of a black hole, not our own galaxies, but a larger one, M87 farther away. Sagittarius A star, despite being much closer, turned out to be a far harder target, its gas cloud flickering and shifting within minutes rather than days. It took years of additional processing, essentially averaging thousands of rapidly changing snapshots, before a stable image could finally be assembled. In May 2022, the Event Horizon Telescope team finally released it, the first image of Sagittarius A star itself, our own galaxy's black hole. It showed exactly what theory predicted, a glowing asymmetric ring of superheated gas surrounding a dark central shadow, the black hole's silhouette. For the first time in history, we could actually see it. The image confirmed Einstein's general relativity held up perfectly, even in the most extreme gravitational environment our galaxy has to offer. It also confirmed something quieter, almost sentimental. The object bending S2's orbit really was exactly what decades of careful math had predicted. What still isn't confirmed, though, is almost everything happening past that glowing ring, inside the black hole's event horizon itself. General relativity predicts a singularity at the center, a point of infinite density where the equations themselves simply stop making sense. Nobody knows if that's a literal description of reality or a sign that our physics breaks down exactly where we most need it to hold. Quantum mechanics and general relativity, our two most successful theories, flatly contradict each other the moment you try to describe a black hole's core. Reconciling them is considered one of the largest open problems in all of physics, and Sagittarius A star sits right at the heart of that question. So the same direction that once produced 72 seconds of unexplained radio noise also hides the most extreme, least understood object in our galaxy. That's not a coincidence of storytelling. It's simply what happens when you keep looking carefully at any one patch of sky long enough. Every layer we peel back out there reveals another layer underneath it, patiently waiting for the next generation of instruments to catch up. I don't think that's a discouraging pattern, honestly. I think it's the whole reason to keep pointing telescopes at the sky in the first place. Sagittarius held a 72-second mystery and an entire galaxy's beating invisible heart in exactly the same direction. We're only just getting started seeing what else is there. We just spent an entire block exploring exactly what sits 26,000 light-years down that same line of sight. But here's the uncomfortable part. Nobody has ever actually confirmed that the WOW signal came from anywhere near that distance. Nobody has confirmed any distance at all. We know the direction. We never actually learned how far. That gap sounds like a technicality, but it isn't. Distance changes everything about what the signal could possibly have been. A signal from 100 light-years away implies something entirely different than the same signal arriving from 26,000 light-years away. One points toward a specific nearby star system. The other points toward the crowded, chaotic heart of the entire galaxy. And Big Ear, for all its historic importance, was never actually built with the tools to tell the two apart. It could only ever tell us which way to look. To understand why, you have to understand what a single radio dish can actually measure, and what it fundamentally cannot. I.e., a dish like Big Ear records direction and frequency with real precision, exactly where in the sky, exactly what pitch of radio wave. What it cannot measure on its own is depth. It has no way to judge whether a signal traveled 10 light-years or 10,000. Distance in astronomy almost always comes from comparison, triangulating a signal using two or more instruments spread far apart across space. That technique is called very long baseline interferometry, and it lets astronomers calculate distance by measuring tiny differences in arrival time between dishes. Big Ear, after all, was only ever a single dish. It had no partner instrument recording the same signal at the same moment from anywhere else on Earth, let alone in space. Even if it had, the signal lasted only 72 seconds. There was no time to coordinate a second observation before it was already gone. So the moment passed, and with it, any real chance of ever calculating exactly how far that signal had actually traveled to reach us. All Jerry Amon could record was a direction, a specific patch of sky near the border of Sagittarius and Chi Sagittarii. Everything past that direction, all the way out to the edge of the observable universe, technically remains fair game for where it came from. That's an enormous range, It spans everything from a nearby sun-like star to the supermassive black hole we just spent an entire block on. In practice, astronomers do narrow that range using context, even without a measured distance, and the narrowing itself tells its own story. The 1420 MHz hydrogen line, for instance, only stays that clean and undistorted over certain kinds of distances through certain kinds of space. Signals traveling through denser regions of the galaxy tend to pick up distortion, a slight broadening or shifting caused by intervening gas and dust. The WOW signal's frequency was remarkably clean and narrow, which some researchers argue makes an extremely distant, heavily obstructed origin less likely, not more. A signal that clean suggests a clearer, less obstructed path. If that reasoning holds, the signal may be more likely to have originated somewhere closer than the crowded, dust-choked galactic core. That would point toward one of the ordinary-looking stars scattered along that same line of sight, much closer to our own solar system. Astronomers have actually cataloged several sun-like stars in that general direction, sitting anywhere from a few dozen to a few hundred light-years away. None of them have ever produced a second signal. None of them have been confirmed as anything more than an ordinary, unremarkable star. But if the WOW signal really did originate from one of them, the numbers change dramatically, and so does the whole shape of the mystery. A signal from 26,000 light-years away is already impossibly old news by the time it reaches us, from a civilization long changed or gone. A signal from 100 light-years away is a very different kind of message, recent, potentially still relevant, from neighbors close enough to actually reach. At that distance, a reply sent today could arrive within a single human lifetime, not tens of thousands of years like the Arecibo message's own round trip. That kind of distance would make the whole mystery feel suddenly, uncomfortably personal, rather than distant history. It's the difference between an ancient echo and a knock on a nearby door, and we genuinely do not know which one we're dealing with. This is precisely the kind of uncertainty Robert Gray spent decades trying to narrow through repeated, careful observation, without ever quite closing the gap. It's also exactly the kind of question modern instruments like the Allen Telescope Array and Breakthrough Listen are built to answer if the signal ever returns. A confirmed repeat, even a faint one, paired with a second dish elsewhere on Earth, could finally calculate the distance the original detection never could. Until that happens, every retelling of this story has to hold two wildly different possibilities open at exactly the same time. It could be a signal from the ancient energetic chaos near a supermassive black hole, transformed almost beyond recognition by the trip here. Or it could be a signal from an ordinary star, close enough that whatever sent it might still exist right now, waiting the same way we are. Both stories start in the exact same 72 seconds. Both remain entirely, stubbornly possible, and no amount of retelling this story changes that single frustrating fact. What changes each time new instruments come online is how much closer astronomers can get to finally ruling one of them out. That's really what all of this searching amounts to, underneath the specific signals and specific telescopes, slowly shrinking a space of possibilities. Not by guessing, not by hoping, by patiently building better tools and pointing them, again and again, at the exact same quiet patch of sky. Somewhere between here and the edge of the galaxy, along that one narrow line Jerry Eman circled in red pen, the real answer is still sitting. It has been sitting there for almost 50 years, waiting for an instrument precise enough or patient enough to finally pin it down. I like that this story still has that kind of unresolved shape to it, honestly. Distance is just one more thing we get to keep wondering about. Near or far, ancient or recent, alien or accidental, the signal did exactly what a real signal does. It arrived, and then it waited for us to catch up. We've spent a long time now tracing one signal outward in every direction it could possibly lead. Into the machinery we've built here on Earth, into comets and hydrogen clouds, and the honest limits of 1970s radio equipment. Into the wider search for anyone else who might be listening back, and the strange, quiet objects that search kept turning up along the way. Every single one of those side paths led us somewhere real. Pulsars that once looked like beacons, bursts of light that once looked like engines, a visitor from another star that never explained itself. a supermassive black hole sitting in the exact same direction the signal came from, 26,000 years of light away. A man who spent half his life listening for an answer and made peace with never quite getting one. A telescope that did its job perfectly once, and then quietly lost its home to a golf course 20 years later. None of the leading explanations, however reasonable each one sounded on its own, ever fully explained the signal itself. Every one of those side roads was real and worth knowing, and every one of them still leaves the original question exactly where it started. That's not a flaw in the story, it's the actual shape of it. A lot of honest searching, radiating outward from one 72-second moment. Most documentaries want to end with an answer. This one, if it's honest, has to end somewhere else. Because the wow signal genuinely never got solved. Not by Eamon, not by Gray, not by 50 years of increasingly powerful telescopes. And I think that's worth sitting with directly, instead of rushing past it towards something tidier. Some questions simply don't close on any schedule we control. Humans are not naturally comfortable with that. We like endings. We like the moment where the mystery resolves and everyone can relax. But most of the universe doesn't actually work on that schedule. It reveals things slowly, partially, and often not at all within a single lifetime. Jerry Eamon died in 2017, 40 years after he circled that printout, without ever learning what caused it. John Krause died in 2004, having built one of the most important telescopes of his era and having lost it to a fairway before either mystery closed. Robert Gray died in 2022, still quietly listening for an answer. 3 lives, each genuinely shaped by 72 seconds, none of them ever got to fully explain. That could read as a sad ending. I don't think it has to. Each of them chose to spend real time on a question that offered no guarantee of ever paying off, simply because it seemed worth asking. That's not naive optimism. It's something closer to patience. The same patience every one of these telescopes has needed, night after uneventful night. Patience doesn't promise you an answer. It just means you're still there, still listening, whenever the answer finally decides to show up. The universe rewards patience unevenly, and it rarely pays out exactly on schedule. Sometimes it hands you a pulsar, and the mystery resolves in months. Sometimes it hands you the wow signal, and the mystery outlives the person who found it. You don't get to choose which kind of question you're asking going in. You only find out by actually doing the work of looking. That uncertainty is uncomfortable, and it's also, quietly, the whole reason any of this searching stays interesting after 50 years. A solved mystery becomes a fact in a textbook. An unsolved one stays alive, gets handed to the next person willing to pick it up. So let's go back, one final time, to the actual night this all started, and just sit with it plainly. August 15th, 1977. A quiet field in Ohio. A telescope built to survey the sky, doing exactly what it was built to do. For 72 seconds, a narrow band of radio noise tuned almost exactly to the frequency hydrogen emits everywhere in the universe, rose, peaked, and faded. It came from the direction of Sagittarius, exactly where this story started. It rose and fell the way a real, fixed source in the sky is supposed to, not the way equipment error usually behaves. Jerry Eamon found it days later, reviewing a printout nobody expected anything unusual on, and circled 6 characters in red pen. 6EQUJ5. A simple intensity code. The strongest reading anyone had ever recorded from that kind of search, before or since. He wrote one word in the margin, almost involuntarily, the way you write something when there's genuinely no better word available. Wow. It has never repeated. Not once, not faintly, across nearly 50 years, and every serious recheck astronomy has thrown at it. Every explanation offered since has been reasonable, careful, and ultimately incomplete in some specific, frustrating way. Earth interference doesn't fit the frequency. The comet doesn't fit the timeline. The hydrogen flare has never been directly observed happening anywhere else. And a message from someone else entirely remains exactly what it always was: possible, unproven, and deeply uncomfortable to either fully believe or fully dismiss. That's the whole file, laid out honestly, the same way it's looked for nearly half a century now. One recorded moment, one narrow frequency, one patch of sky that has never quite finished explaining itself. I'm Ray, and this is where I leave you for tonight, somewhere between everything we know and everything we still don't. I don't have a tidy ending for you, and I stopped apologizing for that a long time ago. Some stories genuinely are better left standing open forever. What I can tell you is that the sky keeps doing this, offering real, careful, half-finished answers and asking you to sit patiently with the rest. Whatever eventually explains the wow signal, if anything ever does, it will almost certainly come from someone willing to keep quietly checking long after it stopped feeling urgent. Maybe that's you someday. Maybe it's just someone listening tonight, half asleep, letting the question drift instead of chasing it. Either way is a fine way to spend it. Space slowly. That's the whole idea behind this channel, and tonight's the clearest example of why. Some nights call for answers. Tonight called for company, while one very old, very honest question kept us gentle company back. Sagittarius is still up there, exactly where it's always been, quietly holding on to whatever it's holding on to. Rest easy. The sky isn't going anywhere, and neither is the question. We'll pick it back up together another night. Good night.